I once again welcome you to MSP lecture series on main group chemistry. In my previous lecture, I was discussing about molecular orbital. While discussing molecular orbital theory, I wrote a general MO diagram for second row diatomic molecules for oxygen, fluorine and neon. Let me write now MO diagram for beryllium, carbon and nitrogen dimeric species, that is B2, C2 and N2. Since I am going to compare the MO diagrams for diatomic molecules such as O2, F2 and Ne2 with B2, C2 and N2, let me write the MO diagrams for both here, so that comparison becomes much easier. Okay. So, here in this case the lower energy one will be sigma 2p, then we have pi 2p and then pi 2p, pi star 2p and then sigma star 2p. Okay. So, and then of course, we have 2 electron in 2s orbital, that also should be considered. This is sigma 2s anti-bonding and sigma 2s bonding. So, like this we can write this is for 2s, this for 2s and this is for 2p and this for 2p. So, this is how one can write MO diagram. This is atomic orbital and this is atomic orbital. This represents the diatomic species O2, F2 and Ne2. The exits are not, that is a different issue, but one can write MO diagram in this fashion and keeping the energy of this in this order. Okay. So, let me write now for carbon, boron and nitrogen. Now, little changes will be there, just remember here sigma 2b is the lower, whereas here pi will be lower, pi 2p will be lower and then sigma comes, sigma 2p and then as usual here no change, pi star 2p will be essentially same and here it is sigma star 2p. Okay, and connect now. Okay, this is 2p, this is 2p. There is no change in the 2s combination. This is 2s, this is 2s, again these are all atomic orbitals, this is molecular orbital for diatomic species. Okay. So, now you can see the difference here in this case pi 2p is much lower in energy compared to sigma 2p, whereas in these cases, okay, that means in the heavier or more electronegative elements in the second row, okay, the energy due to sigma 2p will be lower compared to pi 2p, whereas in the same row group 13, 14, 15 elements we have a opposite situation here. Pi 2p will be lower in energy compared to sigma 2p. Let us look into it why that happens. Before I proceed for that one, I pose a question here. Okay. So, that is we can explain the bonding properties of molecules or ionic species. Okay. For example, let me consider N2 and N2 plus and O2 and O2 plus, and let me look into the bond energy associated with these species and also the bond lengths, that is NN bond length or OO bond length in these species. And let us try to understand from molecular orbital diagram how to explain these properties. First let me write for N2. Of course, now I am not going to write, you know the order. So, simply let me write in the order here sigma 2s and then sigma star 2s, and then I have pi 2p and then sigma 2p, okay, and then pi star 2p and then sigma star 2p. Okay. So, this is for N2 I am writing, and N2 we have total of 10 electrons in its valence shell, that is 1s2, 2s2, 2p3. So, we have totally 5 electrons from each nitrogen. So, we have 10 electrons, those 10 electrons have to be filled here. 2 electrons will go here and 2 electrons will go here and 2 will go here and 2 will go here. Now, 2, 4, 6, 8 and this is it. So, this is how you can show the filling order for N2, and of course, if N2 if I consider here between these, okay, we have 6 electrons, I can calculate the bond order. This is for N2, bond order equals 6 minus 0 by 2 equals 3. So, that means the bond order is 3, that indicates there exists 3 bonds between 2 nitrogen atoms. Okay. So, now let us look into N2 plus. So, N2 plus we are having 1 electron less. Okay. So, here we have 10 electrons we have in this case 10 electrons, and then here we have 9 electrons. So, in the same fashion I will start writing the molecular orbital. Let me start filling now these 9 electrons, 2 electrons here, 2 electrons here, 2 electron and 2 electron and here 1 electron, because N2 plus one is N, one is N plus. That means one nitrogen comes with 1s2, 2s2, 2p3 electrons, that is N. N plus comes with 1s2, 2s2, 2p2 electrons. So, we have total of 9 electrons. These 9 electrons have been placed here in this fashion. Okay, so 1 electron here. So, total we have 9 electrons. So, now if you look into the bond order equals 5 minus 0 by 2, it is equals to 2.5. So, here the net bonding is we have a 2.5. We cannot write fractional bond, but we can say bond is weaker. Okay. Similarly, I can write for O2 here, O2, and O2 you should notice the difference. This is essentially same, okay, and next we have these two are same, 1s 2s2 2s2. Now, we have sigma p here comes and then pi comes here and this does not change, and this is how it is. So, now let me write them. This is sigma 2s, this is sigma star 2s, and then here sigma 2p, pi 2p, pi star 2p and sigma star 2p. So, now in case of oxygen, we have 1s2, 2s2, 2p4. So total we have 12 electrons, we have a total of 12 electrons. So these 12 electrons I will start placing here, 2 here, 2 here, 2 here, 6, 8, 10 and 1 electron here. Okay. So that means 2 unpaired electrons are there. Because of this one, you can say clearly oxygen is paramagnetic and it has 2 unpaired electrons. So one can calculate the magnetic moment mu using square root of 2s into s plus 1 formula, and this clearly indicates why O2 species is paramagnetic. And here if you look into the bond order, we have here 2 plus 6 are there, 6 minus 2 equals 4 by 2, that means the bond order is 2. That indicates we have double bond between 2 oxygen atoms. So verification is correct. Now let me write the MO diagram for O2 plus. O2 plus we have 1 electron less. Okay, so let me start filling here. Here we have 2 oxygen atoms are there. One is oxygen with 1s2, 2s2, 2p4 electronic configuration. Another one is O plus with 1s2, 2s2, 2p3 electronic configuration. So we have 1 electron less. Let me start filling them in the same order. So they cancel each other. They are 4 electrons now. Now you look into here 2. So 2, 2 here. So we have added 10 electrons. The last electron will come here. So O2 plus species is also paramagnetic, whereas here the bond order, if I calculate here, bond order equals 6 minus 1 by 2, it is equal to 2.5. So that means bond is stronger, this is stronger, the bond order increases. So O2 plus will be much more stable compared to O2. Okay. So now we wrote here this MO diagram, and we know the stability using this one. With this, let us look into the bond parameters I told you. What are those bond parameters? For bond energy, I am writing in kilojoules per mole, and also I am writing bond length in picometers. Okay. N2 and N2 plus, and then O2 and O2 plus. Let us compare these parameters now. Let me start writing the values. It is 945, so kilojoules per mole, and for this one 841, and then 498, and then 623, and the bond length is 110 picometer, and here it is 1112, and here it is 121, whereas here 112. Okay. So now we have to explain. I already showed you the MO diagram for N2, N2 plus, O2 and O2 plus. In case of N2, bond order, let me write here bond order. In case of N2 it is 3, in case of this one it is 2.5, in case of this one it is 2, this one 2.5. That means here strong bond, 3 bonds are there, weak, and this is relatively, if I say this is weak, this is strong. Okay. So this information has come from molecular orbital diagram simply by writing. Now if I compare, you see 945 kilojoules per mole, and bond length is shorter because you have bond order 3, a triple bond exists between N and N, and its bond energy is 945 kilojoules per mole. Actually single bond NN bond energy is 160 kilojoules per mole. It is more than 3 times. That is the reason it is more stable. Of course, I will be giving you more details when I discuss the chemistry of group 15 elements, and then the bond length is 110 picometer. Now, N2 plus, you can see bond order is 2.5, that means bond order is reduced, that means it is relatively weak compared to N2, that is reflected in its bond parameter 112, okay, little longer 112 picometer, and whereas its bond energy has dropped from 945 to 841 kilojoules per mole, and same analogy can be extended between O2 and O2 plus. In case of O2, the bond energy is 498 kilojoules per mole, and here bond distance is 121 picometer and bond order is 2. Now, when one electron is removed from antibonding orbital, okay, and now the bond energy increases considerably from 498 to 623 kilojoules per mole, and as a result the net increase in the bond order is from 2 to 2.5. As a result, the oxygen atoms come very close to each other, O and O plus come very close to each other. As a result, the bond distance shrinks and it is now 112 picometer. That means the bond distance in case of N2 plus as well as O2 plus are essentially same. So, you can see how some of these properties can be readily explained simply by drawing the MO diagram, and also the reactivity, all those things one can extrapolate and understand better by practicing and knowing the MO diagrams for most of the molecules we come across. Okay. So, let us look into some heteronuclear diatomic molecules. Okay. So, heteronuclear diatomic molecules, it will be little different. What we should know is, we should know the relative electronegativity of the two atoms that are combining to make a diatomic species. For example, let me consider HF. Okay. This always one should remember to write. So, let me put one S here. This is coming from atomic orbital of hydrogen. Now, if you look into the electronegativity difference between hydrogen and fluorine, there is a remarkable difference is there. So, energy of 2p orbital that is going to combine with 1s atomic orbital will be much lower in energy. So, this will be somewhere here. So, this is 2p and we have 5 electrons. Okay, electronic configuration of fluorine is 1s2, 2s2, 2p5. So, it is in need of 1 electron to complete its octet. So, it combines now. When it combines, it generates 3 plus 1, 4 atomic orbitals are combined to generate 4 molecular orbitals. Out of this one is bonding here. This is sigma, and then here this is essentially non-bonding, because for one, let us say 2pz interacts with 1s atomic orbital to form sigma bond, remaining 2px and 2py we do not have corresponding atomic orbitals from hydrogen. As a result, they do not combine with any of the atomic orbitals we can think of with hydrogen, they remain just non-bonding. So, essentially they remain as non-bonding here. That is the reason there is no net change in the energy compared to the free fluorine atom. And then here we have sigma star. Of course, I did not write here. So, here 2 electrons are there, and this is essentially 2px, 2py. That means pz is combined with this one. This is sigma, sigma star, and these are essentially non-bonding molecular orbitals, atomic orbitals of fluorine and molecular orbital of HF. So, this is how one can write the molecular orbital diagram for heteronuclear diatomic molecule. Here one should remember the electronegativity of 1s is remarkably less compared to the electronegativity of 2p. They have much more lower energy, so that when you are writing you should write in this fashion. Always most electronegative elements have lower energy for the corresponding atomic orbitals, and we have a situation something like this. And here 2 electrons are there, and 2pz combines with 1s to form a sigma bonding molecular orbital, where one electron from this one of the electron from fluorine will be residing to generate bonding molecular orbital, and then the 4 electrons from px and py do not have corresponding atomic orbital from hydrogen. So, they remain non-bonding molecular orbital, and net number of molecular orbitals are still same here 1 2 3 4 1 2 3 4. That means that balancing should be there. So, this is the simplest molecule you can think of as an example of heteronuclear diatomic molecule. One can extrapolate this one to other molecules as well. So, let us try to write for another diatomic molecule, heteronuclear diatomic molecule such as lithium fluoride. So, lithium fluoride case is also very similar. We have 1s2 2s1 electron, and this electron combines with 1s2 2s2 2p5 atomic orbital to generate bonding. Let us see whether we have non-bonding also similar to HF. So, this is 2s, and here it is 2s and then 2p, and now here since we do not have the corresponding 2u, so this also remain as non-bonding, and then we have sigma 2p or simply sigma, and then this is 2s sigma 2s, and then this one remain non-bonding, and then we have sigma here. So, that means essentially very similar to what happened in case of fluorine, lithium hydrogen fluoride. So, this is sigma star. So, here in this case if we consider atomic orbital of lithium, atomic orbitals of fluorine and lithium fluoride. So, lithium fluoride you can explain. So, since 2s do not have the corresponding low energy, so it remains as non-bonding. So, both of these are essentially non-bonding MOs. Okay. So, here whereas this one here essentially one of the 2p orbital, that is preferably 2pz, combines with 2s to generate sigma, where these two electrons are responsible for making lithium fluoride. For example, these 3 pairs remains non-bonding, and of course, one can go to this Lewis dot structure you can see here. Okay. So, these 3 pairs whatever is there that represented here, okay, 6. So, one is this pair, another these 2 pairs, that means 3 pairs can be seen here, and this whatever is there, the sigma 2p, that is responsible for making this bond. So, that means we can take some hint from lithium fluoride Lewis dot structure, and from there we can see we have 3 pairs of electrons are there, it has S2p6 now. These 3 pairs are essentially not at all interacting with lithium, and they are here, they remain as non-bonding. That means some clue can be taken from valence bond theory as well as Lewis dot structure when we are writing MO diagram, and they can be verified. So, once if you are familiar with writing MO diagram for heteronuclear diatomic molecules, you should be able to write for any complicated molecule by considering ligand group orbitals. So, this is a let me write a general MO diagram here. before I conclude this talk. So, this is about 2s. Okay. Of course, here it is sigma and sigma star 2s. Then we consider P, and here it can interchange. Okay. So, here it is essentially 2pz, and here it is 2px and 2py. Okay, same thing here, and here it is pi and sigma and pi star and sigma star, and here it is 2pz, and here 2px, 2py. Of course, I have just considered 2p situation, one can also write 3p and all those things. Okay. So, if it is x atomic orbital and atomic orbital of another x, here it is MO of x2. So, this is how one can write. Of course, this will change depending upon the electronegativity of the combining atoms. So, in my next lecture, I would try to make you familiar with little more complicated molecules. So, have a pleasant reading. Thank you very much.